Good morning. So we are going to study today a very important topic in control system, that is time domain analysis. So in simple terms, time domain analysis is if you have a system, you give some input to the system, you know how the output is. This is very straightforward. The concept is very straightforward. You have a system, say water heater, you are cooking, you are making tea. So the input is you switch on the gas stove, the output is temperature. So when you switch on the gas stove, you are interested in how long it will take the water to boil. That is one direct thing which you want to know. So we'll study this in a very systematic manner, okay? So we studied in the last module the transfer function, g of s. We studied transfer function g of s in the last module. We saw how to find transfer function for simple system. Then we learned how to combine the transfer functions using block diagram reduction and signal flow graph. So in principle, we can find transfer function of any system. There may be loops, there may be multiple forward paths. You will get a transfer function, okay, g of s. So the point is, and we know the definition of transfer function, it is Laplace transform of the output by Laplace transform of the input. So if we know the transfer function, so that is the thing, that is the major point of interest in this class or in this module. If I know the input, can I find the output? So that is what I am going to ask. I know the input. Can I find the output? So after finding the output, can I say something about the system? Can I say the system is good, system is bad, or system is okay, we need some improvement? So these are the things of interest in this module. So I know the input. So the fundamental thing which you learn in this module is you know the input RT, you have to find the output. And since it is in time domain, it is pretty straightforward. Say like I switch on the heater, water heater. So switch on means suddenly I made the flame 100%. So what will happen to the temperature of the water heater, your gas stove? The temperature will slowly increase, isn't it? So if you're boiling water, you know that if you take say, I'll just hold on. Yes, so if I take a vessel, can you see the vessel? Yes, so that if there is some drama, you will remember. If I take this vessel, put it on the stove, then suddenly what am I doing? I am switching on and the flame is there. Then what will I do? Suppose I have a thermometer, or if I look into it, I'll see that the temperature increases gradually, isn't it? The temperature increases gradually. So you are interested to know one thing of which you are interested as something which we'll study later on. You're interested in how long it will take the temperature to reach the required value, say 100 degrees centigrade. Suppose this is my axis. This is time axis. I'm interested to know this time. I'm interested to know when will it reach this steady state. You're interested to know this time. Are you not interested? You're boiling milk, okay? You're boiling milk. You put it on the stove, and then you should, if you know how long it will take for the milk to boil, then things will be easy, isn't it? So boiling milk, you can maybe you can sit in or stand in front of the stove, watch it Maybe if you're careful, you'll have a feel, like maybe 3 minutes, 4 minutes it will boil. If it is, say, full packet of milk, then it will take more time. If you are taking only a small quantity of milk, it will boil easily. So all these things we know somehow. But if it's boiling milk, it's okay. If it's some big reactor, you want to know how long it will take for some chemical to reach some value. It will be interesting if you can find the transfer function g of s, and then you know the input, you can find the output. So that is the agenda for this module. So how do we do it? You know R of t. From R of t, you can calculate R of s. Once you know R of s, you know R of s. What is R of s? Laplace transform of R of t. If you multiply R of s by g of s, you will get what? We will get c of s. And once you get c of s, you can find c of t by taking L inverse of c of s. So it's very important. You can get c of t by finding L inverse of c of s. So I'll repeat this again. So you are interested to find c of t for some R of t. So what should you do? You find R of s, you multiply it by g of s, you will get c of s, which is Laplace transform of the output. Then once you take inverse Laplace transform of c of s, you will get c of t. Is that clear? So in principle, you can find the output of a system for any input. So that is the point which I want to make it very clear. So various types of signals will be there coming to a system. There could be a sudden shock. So your system should be good for sudden shock. I told you about boiling milk. Suppose you think about a car, the input is accelerator and brake. Maybe suddenly you will apply a brake, isn't it? So what will happen to the system? So this is modeled by impulse function. So sudden shock, the system should perform well for a sudden shock. So a mathematical model for sudden shock is impulse. It should do well for a sudden change, and other than shock there is a change. What is change? Say your gas stove was off, suddenly you switch on. So when it is off, the flame is 0. When you switch on, the flame is 100%. So that kind of change is called step function. And maybe you may be applying a change slowly, the input may be changing with time. There could be a linear change with time. That is modeled by ramp function. Say your car is running at 0 speed, and the distance covered will gradually increase if you are going at a constant velocity. So there's a gradual change that is denoted by ramp function. Another input which is of interest is parabolic function. So what are we going to do? Our system should behave well. Our system should behave well for any kind of input. So there are various inputs. So the inputs which are of interest to us are sudden shock, a sudden change, a linear change with time, a faster changes with time. So all these, if the system behaves well for all these kinds of inputs, then the system will be good for all inputs. So from an examination point of view, you should analyze the system for standard test signals. So you should analyze the system for the behavior of the system for standard test signals. So what are the standard test signal? Impulse input, step input, ramp input, parabolic input and sinusoidal input. So the main agenda for this particular class, I give you a general introduction about time domain analysis. In particular, we will be understanding, we will be learning standard test signal, which is easy and which is if you study, you will definitely get for the examination. Okay. So let us see one after another. So this I have already told you. So there is something called ideal impulse signal. This you will come across in signals and systems also. So this is a mathematician's delight. So ideal impulse signal is suddenly what happens, there's a spike. So that kind of signals are called ideal impulse signal. So for mathematician, they can write these kind of equations. RT equal to 0 for t not equal to 0 and equal to infinity when t is equal to 0. So if this is the time axis, then sudden impulse will be something like this. It's a perpendicular line going to infinity, okay, something like sudden impulse. So one good example for impulse is like you go to a doctor, if he kind of to a dentist, if he pulls up your teeth out, that's a kind of an example for impulse signal, okay. Or you are lying down and some baby comes and jumps on your stomach, okay, suddenly like you get a, and another with dentist, like if you have some teeth problem, maybe there may be some spot where the nerve is being exposed. If some sweet or something comes and touches it, you will have a sudden impulse, okay. So I hope you understood it, okay. So one beauty, one great advantage of ideal impulses, the Laplace transform. The Laplace transform of RT is RFS, because we want RFS always. Laplace transform of RFT is RFS, and if RFT is impulse, you know that RFS is 1. This makes impulse signals a great friend of control system engineers and in signals and systems. So 1 is very easy to handle. So practically in impulses, we are engineers. So how will we give an impulse? We will give a signal of high magnitude. You see this magnitude is 10 and short duration. I'll represent it by delta t. So if you integrate it from minus infinity to plus infinity, it should be equal to 1. Then we say it's a unit impulse. If it is 2, we say it's an impulse of magnitude 2. So I have shown here. So practically this is a practical impulse, unit impulse. Suppose the time duration is instead of 0.1, if it is 0.01, the magnitude will be 100. So pallu vedanayude karyam njan paranju. So I told you about toothache. The dentist is pulling out your teeth, okay. So at that small fraction of the time you will have a very high pain. So one another thing which makes impulse such a great friend of control system is, we know that CFS is RFS into, GFS, and RFS is 1. Therefore, what is CFS? CFS is GFS. CFS is RFS into GFS. So RFS is 1. Therefore, CFS is equal to GFS. So isn't it great? And if you take Laplace inverse of CFS, you will get CFT. And what will be CFT? It is GFT. So GFT is sometimes called as impulse response function also, okay. So we'll stop for a while and continue in the next video. Thank you.